Hello everyone. Today we are going to present Morse code decoding and detection using two deep learning models as part of the deep learning course in the Technion. First, we will have a quick look over the objectives of the project and how LSTM-RNN and ResNet can help us solve those tasks. Morse code uses short and long signals called dots and dashes to represent letters and numbers. As we can see, this graph shows the signal in the time domain, while this one is in the frequency domain. We can see that our data is being transferred on main frequency of 200 Hz, which usually refers as pitch. There are a few different types of spacing in Morse code, as we can see here. This one is a space between words, and the other one is in between symbols in the same letter.
The following tasks are supervised and requires labeled datasets, and Morse code labeled datasets are not easy to come by. So our first objective was to generate synthetic data with random parameters like the pitch, the main frequency of the Morse, the signal to noise ratio compared to the signal amplitude, and the Doppler effects, so some physical effects that can stretch the Morse symbols in time. Next, we wanted to decode the Morse content from a spectrogram, and we want to detect the Morse boundaries. So exactly when and where the Morse signal starts in time. For the decoding task, we used a custom-made LSTM-RNN model that we designed in PyTorch. So it starts with a time domain signal, calculate its spectrogram, feed it into a bunch of convolutional layers, so fully connected layers and dropout layers, then into an LSTM with 256 hidden dimensions, and finally to a fully connected layer and an output layer. So this is a medium-sized network with around 700,000 parameters. So what we got so far is a per subframe prediction of the alphabet. And then we use the commonly speech loss function. The connection is a temporal classification loss function to get the final predicted string. In the receiving end of communication systems, it's common to use the SER or the character error rate metric. In our case, we use it for measurements of the model accuracy, and we incorporate the Levenshtein distance into the SER. So it takes into account insertions, deletions of Morse chars for measurement of the model. Here we can see the first 2000 epochs of training, and we can note that after 200 and 600 epoch, we get a large drop in loss, which translates to around 12 million Morse chars that the model saw in training. Here we can focus on the SER accuracy compared to the SNR, and we can see that for above minus 10 dB, which is a very noisy signal, we get less than 2% character error rate, which is a great result. Moving on to the next objective, the detection of Morse code. We use the built-in support in Torch Vision for image object detection, which is ResNet 50 with 40 million parameters, and the RPN loss function, which takes into account two things. It takes into account the categorical loss and the boundaries loss. In the case of digital signal processing, we mainly care on when the data starts and ends. So instead of the IOU metric that is commonly used for box boundaries loss, we implemented the IOU x-axis, which focus only on the time domain. For some results, after around 500 epochs, which is 1 million spectrograms, we got a great results, less than 3% IOU x-axis loss for SNRs above minus 10 dB, which again is great. Now for a little demo. First we generate a random signal with different parameters, so specific string, YouTube, SNR of 3 dB, main frequency 950 Hz. Then we feed it into an LSTM-RNN to decode the content of the Morse. Next, we feed it into a ResNet 50 to detect when and where the Morse code lies in the spectrum.
For future work, we consider more complex physical model for more signal generation. For example, we can see in the spectrogram an original Morse code in harsh conditions. It is more complex to decode since it contains harmonies, pink noise, and spectral leakage. Likewise, we consider a deeper network. We worked with result 50, but to achieve more accuracy, we can try to use the result 152, which will give us more 20 million parameters that maybe will learn more complex dependencies. We can also try for the decoding part a bidirectional LSTM. In addition, instead of guessing the type and the order of layers we used in our architecture, we can try architecture grid search in order to make our model more accurate. Thanks for listening.